more. Okay, action.
Hello, I'm the Great Orbax.
Or am I?
And welcome to Ask Me Anything, Science Edition.
Or is it?
You may have noticed from my incredible intro that there's a degree of uncertainty in today's video.
Or is there?
Yes, there is. Our question today comes from one of our Instagram followers who wants Schrodinger's cat explained. Well, as our resident departmental catistician, I volunteered for the job. To begin, we need to discuss uncertainty and why we're so uncertain. When I look at large objects, I can tell you a few things. I know where they are. Often I know how fast they're moving, or at least that's something that I can measure. I would say I don't see uncertainty in large objects. I'm pretty sure my cat is here right now.
Or is it?
So when do we become uncertain? Consider this. When a particle is massive, and by that I mean macroscopic, I can measure it. I can tell you where it is. I can measure how fast it moves. I can use different techniques, like a ruler or a laser, and get you very, very accurate numbers. In this state, I have a low level of uncertainty. In fact, you'd say I was fairly certain, and physics would behave classically. Well, mass and uncertainty are inversely proportional. When masses are very, very tiny, the uncertainty increases. So think about measuring an atomic particle. Everything we have that can measure that particle will inherently affect its position or its speed. Like a ruler. Or a laser. All these things will affect that particle, and that makes our measurements uncertain. In this case, we would say that the particle no longer behaves classically, that it behaves according to quantum mechanics. Quantum mechanics was formulated in the early 1900s as a way to being actually able to deal with this uncertainty. As you can imagine, not being able to know or measure a particle's position or its speed at a given moment in time actually changes the way in which we do physics. And this is where Schrodinger's cat comes into play. Schrodinger was an Austrian physicist who formulated something called Schrodinger's equation, which was an equation which mathematically treated the uncertainty we talked about as if it was a wave. But when you do that, you run into some problems. Let's call them paradoxes, like this one that was conceived of by Schrodinger. Let's say we have two items, one which is macroscopic and can be treated with classical mechanics, like this cat. And let's take another item, one that's on the atomic level and should be treated with quantum mechanics, like this radioactive atom. So here's the thought experiment. We take the radioactive atom, and if the atom decays, the decay is detected by a device. The device releases a hammer which breaks a vial of poison. We place this inside the box with the cat, and we seal it all up. Now, there's a chance that the atom will decay within a given time frame, but there's an uncertainty as to whether it will or not. See, there's a chance that the atom decays and the poison kills the cat. And there's also a chance that it didn't decay and the cat is fine, but the box is sealed. So how do we know what happened? Well, the easiest thing to do is open the box, and we discover our cat's okay. But was the cat always okay? Well, that's where quantum mechanics takes over. You see, we don't know that the cat's okay until we observe it, until we measure it by opening the box. Hi. So what quantum mechanics says is that when the box is sealed, this cat's in a state of quantum superposition. It's both alive and dead until we make the active measurement of opening that box. And that's not until we open the box that we discover that it's been in that state the entire time. Or has it? Sounds weird, right? Well, that's what Schrodinger's point was. He was actually so disillusioned with the philosophical implications of quantum mechanics that he abandoned it altogether. Now, today, there are two popular interpretations of quantum mechanics. The first is the Copenhagen Interpretation. This one says that all possibilities exist prior to observation. At the moment of observation, the wave function collapses in the most probable outcome, and life goes on. Having always been the most probable state from the moment that we measured, and before. But there's also the many worlds interpretation, where all the possibilities exist. But upon observation, we continue to live in the world where what we observed happened. But then so does another version of us in another world, and another version in another world. As a matter of fact, since there are infinite possibilities in terms of the outcomes of our experiment, there are infinite worlds where each one is a result of one of those possibilities. Now that's strange, and I'm not talking about the quark. For more Ask Me Anything Science Edition, click the links. And if you have a question, go ahead and just post in the comments below. Stay safe and stay science.